Hi guys, I hope all of you are fine, healthy, and kind of happy, let's say. I know it's very difficult times for us, for all of us, and life is going on, so we have to adapt into this new situation. So we have to conduct our classes this way. I think this is the best way to perform this mathematical statistics course. Since I cannot go to the classroom environment, so I'm at home with my kids, and I will try to, continue the lectures where we stopped. Okay, so let me summarize the things that we go through last time, sorry. So we started to see the randomized test. So in the randomized test, we define our null and alternative hypothesis, and based on the criteria that we need to minimize the probability of type 1 error, we need to maximize the power, or we have to minimize the probability of type 2 error. Okay, so what we have, so starting with a random variable x, and we assume that we know its probability distribution, PDF, and we try to get some idea about the unknown parameter theta. Theta can be just one parameter, or it can be more than one. It can be in vector form, and we assume that it belongs to some parameter space. So in the hypothesis testing, we try to define, give some values, or do some hypothesis on the value of the unknown parameter theta. So for that, we have several options. We start with the simplest hypothesis, that we assume that this unknown parameter theta can take just one single quantity, theta 0, versus in the alternative case, theta not taking theta 0 but theta 1 value. So these are numerical quantities, but since we derived the test, we assume that these quantities are like theta 0 and theta 1. Since by assuming that we only have one unknown parameter, so this hypothesis basically defines the whole distribution. So we have theta 0, so there's no unknown parameter in the distribution, so this is fully, completely defined. So if this is the case, the name of the hypotheses are known as simple hypothesis. So we start deriving the testing procedure with this two simple hypothesis case. Then we will derive the best test, or the most powerful test under this condition. And then when we change our hypothesis to the case that theta equals to theta 0, versus we have one-sided alternative. It could be theta greater than theta 0, or theta less than theta 0. Okay, so we will focus on that one. So based on that, basically the testing, we will write the null hypothesis as theta less than or equal to theta 0, or theta greater than or equal to theta 0 way. So basically the result of the test will be the same when we define the null hypothesis in a simple way or a composite way. So this is the case. If we define our null alternative hypothesis in this way, we have infinitely many other choices for the unknown parameter theta. Only restriction is theta should be greater than theta 0. So this is known as composite hypothesis. Okay, so under this type of hypothesis, we will derive now not the most powerful test, but the uniformly most powerful test. Okay, so this can be derived by MPT, and this can be UMPT. Okay, so after that, basically we have not just this type of hypothesis, we might have more than two parameters, and we can only define the hypothesis based on only one parameter, or we can have two-sided hypothesis. So theta equals theta 0, simple hypothesis, versus the composite hypothesis, where theta not equal to theta 0. So in these cases, or we might have two different parameters. Let's say we have theta equals theta 1 0, theta 1, and alternative theta 1 greater than, let's say, theta 1, 0. So if these are the cases and we have one unknown theta 2 under the parameter space, let's say this is unknown, so this parameter is a nuisance parameter if we focus on just one parameter, so we cannot derive the most powerful test. So the test that we derive will not be powerful test, but we can still derive the test. So we will see that this procedure is known as the likelihood ratio testing procedure. So it's kind of a hard topic, likelihood ratio test. So we will define the testing procedure. So we start with the simple hypothesis case, and then the alternative composite hypothesis case, and two-sided case or more than one parameter case under the likelihood ratio test. Okay, so you know, in the testing procedure we have two types of hypothesis, and so two types of hypotheses and two types of errors actually. So one of the errors that we can conduct can be the rejecting the null hypothesis when H0 is actually true. So you know, we are doing some error, and if we define the probability of this event, this error, so this is known as R alpha, which gives us the size of the test, or it's also known as the significance level. And we have another error that we can conduct. When H1 is actually true, we not reject the null hypothesis. We already talked about why we are saying that we are not accepting the null hypothesis, but we are not rejecting hypothesis, so you know the reason. Okay, so H1 is true case. Okay, so this is also an error. Okay, so H1 is true, but we are not accepting H1, but H0. Probability of this event is known as beta. Okay, so probability of type 2 error. So this is type 1 error. Okay, so not the probability but the event itself. So this is type 1 error, and this is our second type of error, type 2 error. Okay, so we want to minimize these errors. Okay, so we cannot minimize both of them, so we discussed that previously. So I'm just summarizing the things. Okay, so what we are doing, so we have to decide on which event is much more important for us, or when we are conducting the hypothesis, basically we are selecting our null hypothesis and alternative hypothesis. So which one is much more important for us? So when H0 is correct, if we reject the null hypothesis, if this is the more important event, or when H1 is the alternative hypothesis actually correct, but we are selecting H0, accepting H0. So usually we have to fix one of them. We have to control one of the errors and then try to minimize the other one. So usually what we are doing, we are setting the null hypothesis in a way that it is the most important event basically. Okay, so the type 1 error is much more important than the type 2 error probability. So what we are doing, so we have to select our null hypothesis based on this principle. Okay, so this one is much more important than the second type of error. So what we are doing, since we cannot minimize both of the errors, we are fixing alpha. Okay, so by this way, basically, we are controlling the level of this error type. Controlling the value of the probability of type 1 error. So this is under our control. So we can give any number that's very small. Usually we prefer like 1%, mostly actually 5% or 10%. Usually we are using these cases. So after setting our probability of type 1 error into this small number, our aim is to minimize beta under this condition. So fixing alpha and try to minimize beta. Or what is beta actually? So we can find the power of the test, which is known as, let's say, power. of the test, we define it by pi function, and in that this is actually 1 minus beta. Or if we write it in terms of probabilities, probability that reject A0, so it's a correct decision, when actually H1 is true. So we are doing the correct decision. Okay, so minimizing beta gives us the maximum power. So maximize power. So this is our testing procedure. For a fixed alpha, we have to maximize the power or minimize the beta value. Under the null hypothesis, the value of the test will be given. If it is simple hypothesis, basically we are just writing the value of theta as theta 1. But for composite hypothesis like this one, so we can have infinitely many choices to calculate the power function, and we can basically find lots of values of theta 0 or power under the values of theta under the alternative hypothesis. Okay, so after that we need to define our test function. So test function helps us to define our hypothesis. So by this way we can define values. So we have to consider the two cases. So focus on the simple hypothesis. Okay, so focus on the case that we have theta equal theta 0 versus theta equals theta 1 case. Okay, so we are giving numerical values to both cases. So under this, basically the probability distribution of the random variable will be f of x, where theta 0 is correct, defined like that. When alternative is correct, then we have this option. I need to change the pen. Okay, so if our null hypothesis is true, okay, so what is the case then if A0 is actually true? Okay, so what we expect when we get the ratio of these, or if we write it this way, we want to see that the density at this point is higher than the density under the null alternative hypothesis. Okay, so if A0 is true case, or I can derive it, give it as f of x theta 0 over f of x theta 1 is greater than 1. Okay, so we don't know the value, so basically we have to decide. Okay, so this is the case basically, but we have to give some criteria. How much bigger? Okay, so if it is like greater, but how much greater? Like 0.0001. So we don't say that it's very big. So we have to define some value k under this case. Okay, so we have to say that if our null hypothesis, the density at the theta 0 is greater than the density of that one, k times, let's say. Okay, so k times. So this will be the criteria then. So we need to decide for which k value this is correct, then we cannot reject the null hypothesis. Okay, let me put it this way. I will also use the back side of the test, but you may need to write everything. Okay, and if H1 is true, so we have the reverse, right? F of x theta 0 should be less than f of x theta 1. So density at this point should be higher. How much higher? So k times again. Okay, so if we write it this way in the ratio type, so this should be less than some value k. So this means that then the density at theta 1, for discrete case, this gives us exactly the probability, you know. So the value of theta 1 is most likely to happen in this case. Okay, so this will be the base actually. So we can do the reverse actually, theta 1 over theta 0 case, but all the testing procedures in the theory of statistics defined by writing the ratio in terms of f of x theta 0 under the null hypothesis over the alternative hypothesis. Okay, so now we can define our our test. So we have the optimality criterion, so we have the test function. So I'm writing the test function just for one single x, then we will generalize it for a random sample. Okay, so let's say this is our test function. Test function to define the rejection rule or the decision rule on the hypothesis. Test function on the decision rule of the hypothesis. Okay, then so we remember the rule that we have. So we have to have fixed alpha. So then the expected value of the test function should be at most alpha, okay, under the null hypothesis. Okay, so this is the procedure. And then maximize the expected value of the test function under the alternative hypothesis. Okay, so this is the optimality criterion that we have. Okay, so this gives us the optimality criterion. Okay, then using that and the facts that we discussed under the null hypothesis, what should be the ratio, and under the alternative, what should be the ratio, we define our test function phi x as, so this represents the rejection rule. Decision rule, remember, the same as the rejection rule. Rejection rule, rejecting the null hypothesis, you know. So it will take value 1, so we will definitely reject the null hypothesis if the ratio of the PDF under the null hypothesis over the PDF under the alternative hypothesis less than some value k. So we don't know that, so we have to find it. And then it will take some value a, okay, if this ratio, the same ratio, equals to k, and we will not reject the null hypothesis if this ratio greater than k. Okay, so this will be our testing procedure. So when we consider the first and the last cases, so everything is clear. So the only thing that we have to decide is the value of k. Okay, but in the middle case, so we have some unknown value a, where we have the equality case. So when we have continuous random variable, basically, you know, the probability of equality is 0. So we will not consider this step. But for discrete cases, so we have to consider this one. So what is a? So here we are conducting a random experiment. Because of that one, this testing procedure is known as the randomized test. So we assume that we are conducting a Bernoulli type experiment with 2 outcomes. And the success probability is defined by the value of the ratio. Okay, so it will take value a with the probability of this one. So when we consider how we can find the value of k is defined by the distribution of x actually. So this is for single random variable, and then when we try to find the value of k, we are using the known thing, the fixed thing. So we already know alpha. So at the beginning of the test, we are fixing the value of alpha. So we know this. So what is the definition? So this is the expectation. Okay. So the maximum value that it can take is this one. Okay. Okay. So we focus on that. So then calculate the expectation. So we know the values that the test function takes and the probabilities of these events. Okay, then we have 1 times probability that this ratio, okay, less than k, plus a times probability of the equality, theta 1, okay, equals to k, plus we have the 0 part. Okay, so we don't consider the other part. So if we know the value of alpha, then we can somehow find the values of k. So for discrete case, basically we are using cumulative distribution functions. For, let's say, for binomial, we are using cumulative binomial function. Or for Poisson, similarly, we are using the cumulative distribution function of Poisson to define the values of k. So we have to define the certain event where, for which x values actually we have to reject the null hypothesis. But for the equality case, because we want that this alpha is a fixed number, at the beginning we stated as, let's say, 5%, we want that this whole quantity will be 5%. For discrete cases, it's not possible always to get exactly alpha probability with just using this part of the probability. So we have to define some random event. If the success probability of this event, random experiment, happens, so we are conducting an experiment with a result of success and failure, and if the result, let's say we have a random variable y under this experiment, if y equals to 1, so this quantity should be a. This quantity, sorry. Okay, so we have two values, and we have to define the success probability of this event. Okay, then with that, actually, we can define the values. So if the probability of the, if we obtain k, let's say, then we have to decide to reject or not reject this null hypothesis. Okay, so value of the a defined by this quantity. Okay, so this will be our success probability that y equals to 1. So we need to decide this one. Okay, so how we can do that? Remember, for some examples, we already solved the Poisson example. Or let me find another example for you for the binomial case. Let me see. Where is my example? Oh, here. Okay, so let's focus on that one. So this is the theoretical one, not the numerical one. So when x is binomial with sample size p and success probability p. Okay, and then let's say we want to test that our success probability p equals to p0 versus the p equals p1, and it is given that the p1 is greater than p0. So it's a simple single quantity, but the value of p1 is greater than p0. So let's try to define the test function and derive the test. Construct the most powerful tests of size alpha. Okay, so this is the question that we have to answer. Okay, so you know the PDF of binomial, and choose x, p to the x, 1 minus p to the n minus x. X can take values 0, 1 till n, and the value of p should be between 0 and 1. So this is the parameter space that we have. Okay, then we have to find the ratio. We have only single random variable here, we assume that, so we will see the random sample case later. Okay, so x under p0 over f of x under p1. Okay, so write the quantities. We have p0x, 1 minus p0, and minus x, and do the same thing for p1. And choose x, p1 to the